up to this point, we mostly have been thinking about gases that are pure, that just have one component in them. But most gases come in mixtures. It's not, well, you can get gases that are pure, but often we're thinking about the atmosphere or things like that, where you have a mixture of different gases. And so in this video, we're going to be looking at how do we account for that. So one of the important ways that we keep track of what's happening with mixtures of gases is through a quantity known as partial pressure. You can kind of think of this like concentration a little bit. And the partial pressure of a gas is the pressure that's exerted by a specific component of the gas. So say for example, we're looking at the atmosphere. Mostly it's made up of nitrogen and oxygen and argon and a bunch of other stuff. But we can think about the pressure that just the nitrogen exerts will have its own value that we call Pn2, right? So just the partial pressure. And if we add up all the pressures of all the different components, the partial pressures, plus all these other pressures, that will just give us the total pressure. So the partial pressure is just a sum, or the total pressure is just a sum of all the partial pressures. And these partial pressures we can find by just using the quantity of the gas that's present. So, say we know the number of moles of nitrogen and oxygen and argon, we can find the pressures of each of those using the ideal gas law, and then if we add all those up, we'll get the total pressure. Now, why does this work? Well, if we look at the ideal gas law, PV equals nRT, when we're looking at mixtures of gases, generally volume is going to be the same, temperature is going to be the same, and R is going to be constant as well. If we're looking at a mixture in a fixed volume, which you sort of have to be if you're looking at a mixture. So what we can do is say that, well, if all of those things are constant, then P and N, they're not equal, but they're directly related to each other, pressure and number of moles. So that means that our total pressure is just going to be related to the total number of moles, and if we add up each of the number of moles of each of the components, that is going to add up our total number of moles. Because these are directly related, all these relationships with moles, which make intuitive sense, right? You just add up the total number of particles, you get the total number of moles, will have the same relationship in terms of pressure. So this is all a consequence of the ideal gas law and the fact that we don't care about the identity of the gas. The ideal gas law works regardless of if you're thinking about nitrogen or oxygen or argon. They all behave the same way. So this is very convenient. It means if we can sort of treat each gas independently, and then if we want to know the total pressure, we can add them all up. A slightly different way of looking at this, and using this equation that we have here, is that if we want to find the total, or if we want to find a partial pressure, we can use a quantity called the mole fraction, not null, it's an M, mole fraction. And the mole fraction is defined as, we give it the symbol x, and say we're looking at the mole fraction of component Z, then it's the number of moles of Z divided by the total number of moles. You can think about it as taking just part of this equation above, right? We know the total number of moles, and we just basically we're saying what percent, not a percentage but fraction, what percent of the molecules in this sample are component Z. So we take the total number then as a denominator and the number of molecules of component Z on the top. So if we wanted this as a percentage, we'd multiply by 100 to get 100%. Right, so this will be some value between 0 and 1. 1 would be if it's only Z present, so it's pure. And 0 being there's no Z present. And then, of course, you'll have things in between those two extremes. So you can't have anything bigger than 1, you can't have anything less than 0. So those are your options for this. And using these equations above, we can show that, we won't necessarily work through the algebra here, it's not too complicated, but we can show that if we want to find the partial pressure of component Z, we can multiply the mole fraction times the total pressure to get the partial pressure. And this is a direct consequence of the equations that we just had above. So if we know the mole fraction, we can find the total pressure, and we can sort of do these go around all the different ways. All right. So now, why is this useful? Well, we can't really selectively measure the pressure of just one gas at a time. If we have a mixture, all we can measure is the total pressure. So this is the thing that we can actually measure, because I have lots of pressure gauges in my lab. I don't have pressure gauges that are sensitive to only nitrogen or only oxygen or only argon. The gauges that I have measure the total amount of gas, right? They measure the pressure of the whole mixture. So we can't measure directly the partial pressures of the gases. But what we can measure is the total pressure, and then if we know the mole fraction, then we can find the partial pressure. So that's sort of in practice how you would actually do this. All right. So we'll go ahead and pause this video here, and in a follow-up video, we'll look at some sample calculations involving partial pressures.